norms on vector space, it's called a normed vector space because you have both of them. So that you have some kind of distance on it, or not distance, but you have size, not distance actually. If you have a sequence, so think of the examples that I gave you that are not R. You can have sequences in R2. They would have two components then. You could have sequences of polynomials. So you could have other things. So every one of those vector spaces that I showed you, you can put a norm on it, and then you can talk about a sequence of whatever object you have. If I was on little L2 of R, what would a sequence in that space look like? This is a hard question actually. If I am on the vector space little L2 of R, what are the objects in little L2 of R? What do they look like? What are they? They're sequences. So one vector is a sequence. So if I have a sequence in that vector space, what does that look like? That's right. The sequence of sequences. So if I have the definitions absolutely the same as you have with absolute value in R, if you have a sequence, and it could be a sequence of sequences if you're on little L2 of R, in a norm vector space, then we say it converges if for each epsilon greater than 0, blah, 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 blah. And in a traditional real analysis class, you will have to memorize this. There's no way around it. You just have to memorize these stuff. I know these definitions. They're not something that's on the front of my mind, like where did I leave my keys? I have no idea right now. They're like ingrained. If someone woke me up and said, hey, what's the definition of what a limit of a sequence? I'd be able to spit that thing out. It's one of those things that probably won't go away with Alzheimer's. Like, I'll still have that in my head. If every convergent sequence actually converges to something in that space, it's called a Banach space. So in mathematics, we like to talk about closed. You might have heard this already, but I'll show you all of mathematics in a few minutes as soon as I finish these notes here. But if every convergent sequence converges to something in that space, you don't leap out of the space when you take that limit, then it's called a Banach space. And Banach is a name. All these people are names. So let me give you a quick example. This little Q is rationals. So if I have the rationals also are a field. So I can have my scalars be rational. Otherwise, it won't make sense. If you go through that checklist of the scalars, if you take a real scalar, then it's going to be like only rationals, then you're going to jump out of the space. So if I take my field to be rationals, that means the scalars come from Q, then it's a norm vector space over Q. So it's got a norm. I can use Euclidean norm there. It will work just fine. E is not a Banach space because I can come up with all kinds of sequences that have limits. They converge, but they converge to something that's not a rational number anymore. And there's many, many examples like this. I can draw one for you on the board. If you take a circle, a unit circle, what's the area of the unit circle? Pi. Right? So pi is not, like that's the first irrational number that most people deal with is pi. But if you take any polynomial and inscribe it inside that unit circle, that area is going to be a rational number. But I can put an octagon inside a unit circle, and that's going to give me that area of that octagon is going to give me an approximation of the unit circle. So if I keep denting the sides more and more, each one of those polygons is going to give me a rational number. But the areas of all those polygons are going to converge to pi. I don't know why I chose this one. This is the one that you should do in calculus. You might not do this one here in calculus. But in calculus, you'll prove usually that this limit is equal to E. So every one of the ends that I plug in here is going to give me a rational number. So all of these sequence members themselves are rational numbers. But when I pass to the limit is no longer a rational number. I think I did prove it here at one time, and then I realized I shouldn't do that because it was just not something we should be doing. It was not in the class. Engineering math is Python, where infinity is equal to 1,000. I don't want to hurt Colonel Blumen's feelings, but he's a mechanical engineer in our department. But infinity is equal to 1,000. Just run it on Python, and you will actually see. You can put it on Excel. And you'll actually see that if you take 1 plus 1 over n, let n start to go up in value, you'll see it converting to what the calculator would say is E. Speaking of calculators, the reason calculators work is because we say the rationals are dense in the reals. Every real number has a sequence of rationals that converges to it. That theorem is a big theorem, and it's used by your calculator. That's why it can do approximations. It knows it's okay. It knows it's not a weird thing. Like it'll approximate E for you, and it'll know that's okay.
You said one more time.
The rationals, the word is dense. That comes actually from topology, but every real number can be written as a sequence of rational numbers, as a limit of a sequence of rational numbers. Every real number can be. So the real numbers is a norm vector space that is a Banach space. In fact, this is again what I'm saying, that we actually put this line over it. Let's say I take the rationals. It's got all these holes in there. You can't see them anymore, but I write out you already know the rationals are countable. So they're exactly kind of like the integers. But there's a bunch of holes in there, and the holes are the limits of sequences. Like square root of 2 is not in there. And square root of 2 can be written as a limit of a sequence of rationals. So think of the number line with these little holes all over the place. People can't see them, but they're there. Pi is in there. E is in there. There's a whole bunch of little holes all over the place. In fact, there's an infinite number of holes. Just people can't see it. If I close up all those holes, I get the reals. So the reals are what we call the completion of the rationals. If I fill up all those limits, I get exactly the real numbers. The real numbers is a artifact. So I'll do that in a second, but it's an artifact of taking limits. So on the next homework, I'm going to try to make the next homework light. You can pretty much follow what I did with 1 over n. I'm going to give you this one, just a 2-component sequence, just so you can see what a limit looks like with a norm, a couple norms. So the thing about the norms that I've shown you is that if you converges in one norm, it converges to the other one. So we say that the norms are equivalent. So convergence is all you care about in real analysis. If I had to describe real analysis in one word, it would be limits. That's what that class is about. So I'll put up the next homework today. What I'm going to do also is I'm going to have you revisit the problem that you gave me, that you said, hey, I looked back at that and I think I understand it a lot more. Don't worry, I'm not going to ask you to redo it. I think I already gave you the solutions for it too. I just want you to go back and remember what it was that was so hard at the beginning. It'll be good for me as a teacher to see that too. And then go back and say, now I understand these things much more clearly, and here's why. It's good to take a little check and say, we're actually learning something. We're growing. Otherwise, it'll feel like you're just checking the box every time and doing another homework. So this one will be fairly light. You can follow what I did with I think I did 1 over n in here. You can follow what I did and it'll match up. Okay.